The last topic I want to talk about, so far, how many dimensions have we dealt with? One. We don't really see one-dimensional objects a lot. We're going to talk about 2D systems. Okay? You can extrapolate 2D to 3D. This is kind of strange because you would think the complexity would just increase and make things way more difficult when it comes to three-dimensional systems. But really, if you understand 2D, you got 3D. No problem. Okay?
It's not like calculus where 3D is special.
It's still special, and there's other stuff that I'm not telling you. But if you understand 2D, you can look at 3D systems and get what's going on.
So with 2D hydrogen, like a square.
Yep. We're looking at a square lattice, hydrogen chain. Yep. Yeah, basically, yeah. Let's consider a 2D square lattice. Hydrogen atoms. With lattices AX and AY. Okay, what do we know about AX and AY given we're on a square lattice? Yep. AX is equal to AY, but we want to distinguish them apart from one another for a reason we'll see in a second. So here's our square lattice. Okay, we got to draw our vectors. I want this way to be X and this way to be Y. My next question to you, how many wave vectors? Do we have? Yep, we got two. What are they?
Is it just KX and KY?
Yep, KX. That should be a lowercase k, by the way, and KY. Okay, this range is AX. That way is AY. Everybody feel comfortable with that? Okay, the next question I'm going to ask, which you may not know or be able to explain quite yet, but you will eventually. What does the Brillouin zone look like?
I would assume it goes negative 2 pi over.
What?
It's like a big thing.
A big thing.
You go from negative 2 pi over A to 2 pi over A. That's only for units of 2 weeks, though.
Okay. What was it? What was its shape for a 1D system?
It was sinusoidal.
Yeah, it was sinusoidal. What is that, though?
Oh, like
Which? Sine curves? Yeah, so what I'm trying to get at is what is the shape? A geometric shape, when I draw something like this,
That's a line.
it's a line.
Oh, so it's going to be a square.
This is a square. Yep.
Okay.
It's a square. Oh boy. I like squares. They're the best geometric shape. My daughter will argue with me every day. Triangle.
To be fair,
They're the strongest
No,
shit.
triangle is a good shit.
triangle is good.
Can we all agree we don't like hexagons?
No, my youngest daughter does, and that's why there's problems there.
Hexagons are awful. Makers are great. Hexagons are great.
Yeah, I like
Yeah,
hexagons.
I like hexagons. But I hate hexagon tiles in a room. You're trying to walk and count, and it's just terrible. You see fractions everywhere. Disgusting. Yep.
I like
The worst shape, though.
Hexagon.
Nope. Quadrifolds.
What are those?
Clovers.
Oh, they're annoying.
That's.
Circles. Disgusting.
They're not real.
Yeah.
It's like birds.
Anyways, back to what we were trying to do. That's not. It's like birds. I love that.
it's just
Okay.
like the spherical earth.
So in the square, the spherical earth. Man, you really want me to get me on a rant. We got a square. In the square, we have what are called special points that we're going to denote. They're special spots in K-space. Depending on the lattice, you have unique or selected special points. I'm going to draw. That's our Brillouin zone. We have one point in the dead center where each of our K values, Kx and Ky, by the way, we're going to denote their directions right now. That way is Ky. This way is Kx. Remember, we're in reciprocal space. What's the value of Ky and Kx here? Yep, it's 0. We call this special point the gamma point.
Oh, I see that.
Mm-hmm. Gamma.
That's what they're on about.
Wait, why did you
Capital, yep. Now this point, we're going along which vector? K sub what? X. This point here, what's the value of Ky?
0.
0. What's the value of Kx? We haven't talked about it yet, but for a 2D hydrogen chain, yep, pi over A.
I over 8 ends.
Yep. We're going to give this symbol fancy X. Yep. Now, symmetrically, are these, I'm going to have another special point here, are these two different?
No.
No, they can have different wave vectors, but symmetrically, they're not different. That's where we give this one the same label. Yep. Now, let's say we weren't on a square lattice, we were on a rectangular lattice. It would be fancy Y at that point. We would change it up because the lengths are different and they're not symmetrically equivalent. There's one last special point here. Does anybody know where it would be?
In the corner.
Yep. What would the value of Kx and Ky be there?
Pi over A.
Yep. Pi over A for both. We give this the symbol fancy M.
Why?
I have no idea why. It's just another, we ran out of symbols. There probably is a reason for it. It's probably after some scientist, but honestly, people change the labels of these, and it's really just a marker of where you are in K-space. So if you look at publications, a lot of times they'll draw the Brillouin zone and they'll label these just so you know what it is. Okay. Yep.
Okay.
Go ahead.
I know you said we're not talking about 3D, but if we're in 3D, would
Yeah.
M be in the corner for Z, Y, and X are all
It would really depend on the unit cell. And there's multiple points there.
okay.
So really it's kind of user defined at that point. Some people say there's explicit ones, and other people go, I label it, it's fine. Okay.
Just into a triangle, but from the
Yeah.
like from the center to the end using the wave vectors, or is that not really?
Oh no, that is a thing. And that's actually what the band structure sort of is.
Oh,
Okay? For these systems. The band structure is going to get a little wonky. Okay? All right. Let's make this note. Note. Okay, the wave vectors both have a special point. Fancy X. And why do they both have X?
because they're degenerate?
Yeah.
Because square.
Equal.
Yep, because of square due to symmetry. If that symmetry were broken, what would happen?
They would have different ones.
Yes. Okay, keep that in mind for your daily problem. Don't sound so excited about it. Okay, next thing we're going to do, we're going to draw the block functions at each of these points. Okay? Am I cool to erase this whole thing? All right. Would it be cool? I know I'm cool. I don't need to worry about that. Yeah. At gamma point, what did we say the value of these wave vectors was?
0.
Yeah. Okay. X, Y. Zero and zero. What did the block functions look like for a 1D system? Yep. They looked bonding. So they're bonding in the X direction. What are they in the Y direction? Yep. So then if I keep propagating that, that's what I'm going to get, right? Okay. What about at X? And in this case, I'm going to say Kx is equal to 0. Ky is equal to pi over a. And remember, we're going in that same direction. So along the x-axis, how should I draw it if it were a 1D hydrogen chain? Mm-hmm. Yep. Mm-hmm. Yep, they're all the same. Now, let's consider the y-axis. If we're going to draw a line in this direction. Yep. They're out of phase with one another. They're anti-bonding. Now, what about as we propagate along this lattice direction? Yep. What about this one? Or as we go this way? Yep. Now I want to eat Oreos. It's okay. Get some Oreos, you crush them up with cream cheese, then you dip that in chocolate. Oh, so I do too, but it's good and stuff. Okay, that's that special point, but now let's look at k is equal to pi over, kx is pi over a, and k 0. Ky is 0. Geez, talking. Going along the x direction, what do I need to do? Yep, alternate. So it's anti-bonding along the x direction. What about the y direction? Yep. So what about for this guy? That one right there. Yep. This one's also shaded, right? Yeah, I jacked it up pretty bad.
He's alright.
It got distorted.
Yeah,
Jan Teller.
yeah, it got Jan Tellered. Okay, now let's say kx and ky are both equal to pi over a. What has to happen in this direction? Yep. What about in the y direction? Yep. Okay. My square is looking great. Okay. We got to keep this going. Shaded or unshaded?
Unshaded.
Shaded or unshaded?
So is this
I
M?
can't.
Shaded.
Wait, so is this M?
This is M. The last one I want to draw. Yep. Pi over 2a. Almost like it was planned, right? Okay. What does this mean?
So now, when you go in the y direction, there's going to be a node.
Yep.
And then there's going to be one of the opposite direction. But I don't know what's going to happen in that middle.
So, what goes on here?
It should
Across.
stay the same.
Yep.
Can you just have the middle full of the nodes?
Yep.
Oh boy,
That's kind of awkward.
I don't like it. Please do. I don't understand what it is.
There's no character in between. Because we're at pi over a. Pi over 2a, excuse me.
I'm going to go on a limb and say that ax is equal to pi over 2a and just that.
Yes. Now, ky, pi over 2a. They're both equal to pi over 2a. So, Lily, that's where, oh, I lied to you guys. That's not the last one. That's where we would be drawing a triangle in reciprocal space. We'd be out in a different spot. What's this one going to look like? So if I have that there,
Then it's a node,
yep,
and then it's shaded.
yep. We got to do the same thing here, right?
Then it's a node, shaded. Can you do the outside of the circle first?
Sure.
And then it's a node, and then it's not shaded. And then it's, yeah, then that one's a node, and then it's not shaded. And then, I don't really know it.
Shaded.
Why?
Well, could it be unshaded also? Yeah, they're degenerate in this case. Yep. I like shaded in the center, but they're degenerate. Now, if these lengths were not degenerate, yeah,
Weird stuff.
yep. And then you would have to consider, okay, is the bond shorter or longer here? What's the quality of overlap? Yep. So those are what the block functions look like. How are we doing on time? Yeah.
We have 5 minutes.
Perfect. Am I okay to erase this? Cool. Okay. So now, what does the band structure of this thing look like? Sorry, I fill them up pretty quick. So you draw on the 1D hydrogen chain. You don't have to draw this one a ton, but really, we went K, X went from 0, A, we had energy, and we did that, right? Now, really, this point here, what is that a plot of? Going from what to what in terms of our special points that we have?
The middle
Mm-hmm. So gamma point to fancy X. Yep. It's nothing too crazy. These are the points that we would have for the 1D system. But now, what do we got to worry about? We have a bunch of different directions we could move in reciprocal space. If you wanted to know what that would look like, you would get what's known as a Fermi surface. And you could look at, see what does that look like on a plotted system. However, people like to look at a two-dimensional plot of the energy and as we're moving through K-space. So what ends up happening is it really depends on the order that's selected. So it depends on the selected order. Of special points. That's why if you look at most publications, it draws what are those special points in the Brillouin zone, and then they indicate which way they're traveling. We could pick any way we want, but what we're going to do is we're going to choose going from gamma to fancy X to M, fancy M, back to gamma. Generally, you try to be cyclical in your band structure. We're going to plot E. We're going to go from gamma to X to M and back to gamma.
Okay, so I've seen these publications before.
That,
Yep.
okay. Why don't we just do a contour plot?
You could.
I don't know. I say it as a joke because one
Yeah.
contour plots by hand.
Yeah. Oh yeah, by hand it would suck, but people like to do it this way too, because there's important features such as indirect band gaps, which are important for a lot of semiconductors, such as graphene. All right, let's look at these values. What is the most bonding state we're going to have at all of our special points? Yep, at gamma. So, and we got to match it back over here. Where is the most anti-bonding situation? Yep. Yep. What about at X? Where would you place that one? Yeah, in the middle. So we would plot this out. This is pretty representative of the 1D hydrogen chain, just in reverse. Okay? So now I get questions on what should I plot? How should I plot it? What should I do? That's user preference.
Are the gamma to X like supposed to be like a sigmoid, like X to M?
Yeah.
Okay.
It's just kind of like the other one, but the first part is kind of
Yeah. Okay, from this, you can get a DOS too. Plot it, tell what it is. What's most important would be to consider this for the DOS, because that's where it's unique. Here, this is actually not unique. Going from M to gamma. Okay, now you know about all you need to know. Yeah, Devin.
And when we're plotting energy with respect to these special points, are we compressing the two-dimensionality into like a single coordinate? Like kx, that represents kx and ky simultaneously.
In this case, yes, we are, because of symmetry reasons, but you would normally have another thing along here. Like you would have a y.
Sorry, could you repeat that last one?
So if kx and ky weren't equivalent due to symmetry reasons, you would introduce another special point.
Okay.
So we would have like y
Okay.
if we were in a rectangular system. And then you just pick which direction do you want to go.
Would you do like a goofy 3D graph where like, okay, so in the
Mhm.
flat part of the graph,
Yep,
one way is x and one way is, well, kx and one way is ky and then up is everything.
yep, and that's where the contour plot would come into play.
Well, you could plot in 3D and get the surface, or what you could do in your case is you just, like with a contour plot, you just squash everything down and you can color or you can draw like lines.
Like a topographic.
Yes, exactly. It would be a topographic map.
That would give you the energy.
However, it's more common to just see three-dimensional systems plot a Fermi energy, and they say, I'm going to plot this energy and see what it looks like. And usually around the Fermi level, so you can see what it looks like.
People are notoriously bad at interpreting three-dimensional graphs, so
How would you do a 3D graph?
It's actually just a three-dimensional surface.
Oh.
Yep, and you just pick points of what you like. All right, good discussion. Next time we're going to calculate stuff. Have a good day, everybody.